Welcome friends for the lecture on design of clutches. Basically, the clutch, it is a mechanical device that engage and disengage the power transmission, especially from driving shaft to driven shaft. We know that the clutch, it is always in between the engine and the gearbox, so that whenever we require to change the gear, we have to disengage the driving shaft from the driven shaft so that we can change. Now, which are the main components involved in the clutch? That are the driving members. Driving members has a flywheel which is mounted on an engine crankshaft. A disc is bolted to the flywheel which is known as a pressure plate or the driving disc. Under the driven member, it is called the clutch plate, or it is also called the friction plate. This plate can slide freely to and fro to the clutch shaft. That shaft is called the spline shaft. And the operating member, that is the paddle or the lever, which can press to engage and disengage clutch. There are different types of clutches: mechanical clutches, pneumatic clutches, hydraulic clutches, and electromagnetic clutches. Under the mechanical clutches, there are again two types or two classification: positive contact clutches and the friction clutches. Under the positive contact clutches, jaw clutch and the tooth clutch. Under the friction clutches, there are disc clutch, cone clutch, and the centrifugal clutch. Under the disc clutch, there are two types: the single plate clutch and the multiple plate clutch, which here you have to design the single plate clutch and the multiple plate clutch. You can see here, this is the schematic diagram where this flywheel is mounted on a driving shaft, and the pressure plate, it is bolted to the flywheel itself, and the frictional plate, it is mounted on the driven shaft, which is spline shaft. You can see the races over the shaft. So, and because of the spring force, always it is in the engaged position. When we press the paddle, it retracts. So there is a difference, there is a distance between the friction plate and the pressure plate, and the power transmission stops. So this is the single plate clutch. And in the multiple plate clutch, here the size of the multiple plate clutch, especially the radial diameter, is less. We are accommodating the more number of surfaces, so that's why the diameter is less. So there are number of plates, more than 2 plates mounted on a driving shaft and more than 2 plates mounted on a driven shaft. That's why it is called the multiple plate clutch. Now we'll see the design. We take, suppose the power transmission or power transmission capacity is 8 kilowatts. We have to design the clutch in such a way that it will be able to transmit 8 kilowatt power at 1000 rpm, and the frequency of operation of the clutch is 80 to 100 times in a 8-hour shift. So always first you have to design, whenever we call it as a design of clutch, first always you should have designed the input and output shaft, especially the output shaft. The selecting material as C45, or you can say the plain carbon steel C40, C45 for the shaft. Here we select the C45. So yield stress for the C45 is 360 Newton per mm square, and from that you can find out the shear stress, which is we are getting 45 Newton per mm square. Now you know the power, so we can find out the torque. Torque transmitted T, it is equal to P into 60 divided by 2 pi n. By that you can calculate the torque, and then you can convert this torque into the design torque. Now here, especially in the clutches, the design torque, when we talk about the design torque, this for converting this calculating torque or the average torque into the design torque, you have to multiply by kW, and that kW is K1 plus K2 plus K3 plus K4. This equation is available in PSG on page number 7.89. K1 is what? K1 is the driver shaft dynamic characteristics factor. K2, it is driven shaft. By mistake it is written driver, but it is driven shaft dynamic characteristics factor, which is 2.25. K3 is a wear factor, and K4 it is a frequency of operation. So you know this data is available in the PSG on page number 7.90. You take that value from the PSG and calculate the kW and then multiply this kW to the average torque, you will get the design torque. Now from this design torque you can find out the diameter of the shaft. Now we know that if any torque is acting on the shaft, the shear stress will develop, and for that equivalent torsional equation is the design torque, it is equal to pi by 16 tau into d cube. So you know the design torque, you know the value of the tau, so you will get the value of the d. Now this d we are calculating only considering the torque. We are not considering here the bending moment. Definitely the bending moment will occur, but we don't know here the weight of the part which is mounted on the shaft. So we are not able to calculate exactly the bending moment. So therefore, once you calculate the diameter, modify that diameter on a larger size so that you can consider the effect of the bending also. And that's why you have taken d, it is equal to 36. Now 36, it is a standard value, and that what are the standard value that are available in PSG on page number 5.30. So with reference to that we are taking here. Now once you select this d, this is d, it is the minor diameter of the spline shaft. For spline shaft always there are splines, so outer diameter is definitely be greater than the minor diameter, so that is 40. So this is again you can select from the PSG. In PSG that data is available, so whether the splines are 8, 6, 10 for the 36 mm diameter, so accordingly you can select, and we select the standard spline shaft, it is 8 by 36 by 40. Then the next very important part in the clutches, that is the design of the friction plate. Now here the thickness of the friction plate is not more than 1 to 3 mm. So therefore first assume that the thickness of the plate it is equal to 3 mm. Then how to calculate the outer diameter and the inner diameter of the friction plate? So generally there are standard proportions. So R minimum it is 2D and the R maximum it is 1.5 times the R minimum. So by that relation you can find out R minimum and R maximum, and once you get the R minimum and R maximum, then the difference of these two, that is the width of the friction plate. So that also you can calculate. Then you can calculate the mean radius that is required for the further calculation, and therefore here itself you calculate that mean radius R maximum plus R minimum divided by 2. Now once you get this, again we require the allowable pressure PA, it is equal to K into PB. Now what do you mean by, what is K? K, it is the speed factor, which is point. Now how we are getting this 0.63? So for that, for getting the speed factor in PSG on page number 7.90, there is a graph. From that graph, if you know the linear velocity, you can find out this K. So how to calculate this linear velocity? V is equal to 2 pi n by 60, that means it is omega into Rm. So if you substitute the value of n, here again it is by mistake it is written 1500, that should be 1000, means 1000, multiply by Rm is 90 into 10 raised to power minus 3, because we are converting here into mm to meters, so that you will get the velocity in meter per second. So with the help of this value you will get the value of K. Now then for allowable pressure we want PB also. Now for PB again in PSG on page number 7.89 there is a data. Consider some conditions there. We consider the compressed asbestos on steel. So if you consider this, then PB it is 2 kg per centimeter square. So we can convert into Newton per mm square, 0.2 Newton per mm square. So allowable pressure PA, if you substitute the value of K and PB, you will get 0.126 Newton per mm square. Then we have to calculate the minimum number of the friction surface. So for that we have to assume the coefficient of friction. So coefficient of friction, we will assume that here it is 0.3. Now this I minimum, this is the minimum number of friction surface to transmit the power. Now this is for the multiple plate clutch. If it is single plate clutch, then you have to assume that I minimum it is equal to 1. If both the surfaces of the friction plates are active, then I minimum it is equal to 2 for the single plate clutch. Otherwise, if it is multiple plate clutch, you have to find out the I minimum value. So how to calculate this? This equation is available in PSG. I minimum it is equal to the design torque divided by 2 pi PA B mu Rm square. Substitute the value, you will get I minimum. Now once you get the I minimum, then this is in fraction. So we know that the I minimum, it is the minimum number of the friction surface. So number of the friction surface must be the complete value, and therefore we are converting that, we have modified that into the complete number. So I minimum will become 5. Now when we are taking I minimum 5, definitely the allowable pressure will change. So that you have to find out, and in further calculation you have to take the new allowable pressure. So that's why here it is written I minimum it is equal to 4.389. That means for I minimum 4.389, the allowable pressure is 0.126. Then if you are taking I minimum 5, what is the allowable pressure? Thus the plate should be arranged in such a way that now we have taken, we got the 5 number of minimum surface. So we know another equation, that is I minimum it is equal to m1 plus m2 minus 1, which you have seen in theory of machines, in the theory of clutches. So from that you will get m1 plus m2 it is equal to 6. So that means 3 plates are mounting on the driver shaft and 3 plates are mounting on the driven shaft, right? So this is the design of the friction plate. Now after that, the important part is the design of the lever. In this design of the lever, actually we are not designing the lever, but we have to design the lever pin, because that is the critical part and that will fail. So that's why again we'll start from the number of the levers, how many number of levers it is required. So in PSG the data is given that 3 number of levers it is required for the clutch. So we have taken 3. Axial force Q it is equal to PA into pi into R maximum square minus R minimum square. So if you substitute the PA, R max and R minimum, you will get the Q. Now Q is what? Q is the axial force. It is generated by the spring. Now the force on the lever, definitely, see this total force will act on the lever. Now there are 3 levers, so definitely the force on each lever, it is total force divided by the number of the operating levers, so which is 3. So that from that you will get the Q dash, it is 750.53 Newton. Now this Q dash, you can see here in this diagram, this Q dash is acting horizontally, right, and at distance A from the center of the pin. So whatever the circle you can see here, that is there we insert the pin, so that is the lever pin. So that we are going to design. So here Q dash we are getting. Now you can calculate the Q double dash, and that is by considering this dimension. Suppose A it is equal to 40 and relation between A and L, it is 3 times the A. L it is equal to 3 times the A, then length of the lever L you will get 120 mm. So length of the lever means it is the distance from the center of the pin to the perpendicular distance up to the Q double dash. So Q double dash you will get Q dash into A by L, that is 250.17 Newton. Now once you get this Q dash and Q double dash, you can find out the reaction on the, because you can see here there the Q dash is acting horizontally, Q double dash is acting vertically. So the resultant, it is always the under root of the Q dash square plus Q double dash square. So you substitute the value, you will get the value of A, that is the reaction on the lever pin. Now if you assume that the material for the lever pin is it is medium carbon steel, then the tau it is equal to 300 kgf per centimeter square. So For this, the equation for the diameter of the pin d1, it is equal to 0.046 under root of a. This is again available in PHE on page number 7.90. If you substitute the value of a, you will get the d1, and that d1 you are getting in centimeter 0.409 and in mm 4.09. That means if you take a pin diameter is more than 5 mm, so that will be the safe for this. And then again one more important part in the clutches, that is the spring that you have to design. Now you know already in machine design 1 you study how to design the spring, but now this spring you have to specifically design for the clutch. So assume the number of spring 6. We know here the minimum force on the lever which you have calculated here, which is 750.33 Q dash, right? Force on each lever. Now that minimum force we are considering 755, and from that you can calculate the maximum force required, that is F P, it is equal to F minimum plus QR. F minimum, it is the minimum force, Q, it is the stiffness of the spring, and gamma, it is the displacement. Now we should know the stiffness of the spring. Now how to calculate the stiffness of the spring? For that you have to assume the spring index, C, it is equal to 6. Assume the number of the turns, it is equal to 4. Select the material for the spring, it is grade 4. Now this material and all, it is available in PHE on page number 7.105. So from that, grade 1, grade 2, grade 3, grade 4 materials are given. Here I have selected grade 4, diameter of the wire is 4 mm. So average value of the tensile strength, it is 188. Now for this grade and for this diameter, the average value of the tensile strength is 188 kgf per mm square, or 1880 Newton per mm square. Now if you know this data, you can find out the stiffness. Stiffness Q, it is equal to G into D divided by 8 C cube into N. G here, it is the modulus of rigidity. Now material is grade 4, which is steel material. So for steel we know that the G is 0.84 into 10 raised to power 5 Newton per mm square. D, we have assumed that it is 4 mm. C 6, so cube, and N, it is the number of the active coils, we assume 4. So Q you get 60.76 Newton per mm square. Assume the pressure plate. Now we want the distance between the two plates, that means the displacement during the disengagement. So assume that 2 mm, 1 mm or 2 mm is sufficient for the disengagement, right? And from this we can find out the maximum force P. This is equal to F minimum plus Q into gamma, right? So 890 Newton. Now we know the in question expected number of cycles to be completed by the spring is 80 to 100, it is given per shift. So number of cycles per year, how to calculate? Suppose there are operating cycle is 100 time in 8-hour shift and per day 1 shift, right? So in a year there are total 365 days. Out of that, suppose 65 days are off and all, so we'll consider 300 days operating. So 300 into 100, that will become 30,000. So number of cycles per year, it is greater than 10,000 but less than 10 raised to power 6, right? And therefore the tau design stress, tau, it is equal to 0.324 sigma e. So this is according to this number of cycles, and this is available in page number 7.102. So if you substitute sigma u, which I have selected already, so you will get the tau, that is the design stress. Now once you know the design stress, then you have to calculate the induced stress, how much the stress induced in the spring, and that induced stress should not be greater than the design stress, right? So if the induced stress are less than the design stress, you can say that your design is safe. Now how to calculate this induced stress? For that you know the formula which is available on page number 7.102. Tau, it is equal to 8 pi Ks P into C. That is not PA, consider that is P. P means the maximum force, right? 890 Newton. So if we substitute, now what is the value of what is case? Case is the wall stress factor, and this wall stress factor you can find out according to the spring index. So this is available on page number 7.100. One graph is given there. So for C6, what is the value of case? And that is 1.25. You substitute that value in this formula and calculate the tau. This value of tau should not be greater than 609.12. If it is less than this, you can say your design is safe. If it is greater than the design tau, then again you have to change your assumption and start the design. Thank you very much.